Hey there, quick screencast on an application of Bayes' rule, this one to a problem about M&Ms. In 1995, Mars Incorporated, who makes a lot of American chocolates, including M&Ms, changed the colors of candies in a bag of M&Ms. This table here shows the color distribution in 1994 and in 1996. So before the change, here's the distribution. Notice there were no blues in 1994. In 1996, notice they add blues and they take the tans away. And you can also see that the proportion of the other colors also changes. So here's the question. Suppose I have one bag from each era. I pick an M&M from each bag and don't tell you which comes from which bag. I get a yellow M&M from the first bag and a green M&M from the second bag. Here's the question we want to answer. What's the probability that a yellow M&M came from the older bag and the green M&M came from the newer bag? There are two possibilities. We'll call them hypotheses. Hypothesis A, the first bag is the old bag, the second bag is the new bag. Hypothesis B, the first bag is the new bag, and the second bag is the old bag. We will assume both possibilities are equally likely. So there's a 50% chance for either hypothesis. Let E denote the event that has occurred, that is, the choosing of the M&Ms. The yellow M&M was drawn from the first bag, that a green M&M was drawn from the second bag. What we want to know is what's the probability that hypothesis A is true given how we drew our M&Ms. So that's this conditional probability. Bayes' rule says the conditional probability we're interested in can be written in this way. So the numerator is the standard way to write the numerator. You're flipping these events and then multiplying by the probability of the event A in this case. And downstairs, we're using the two possible hypotheses. One of the two has to occur, so they exhaust all possibilities. So we're going to divide the denominator into these two hypotheses. So what's the probability our event occurred under the first hypothesis? And what's the probability our event occurred under the second hypothesis? We know the hypotheses are equally likely, so that allows us to fill in these probabilities, which I've done here. To complete the computation, we need to calculate this and this. The first is this conditional probability, and it's the probability that I draw a yellow candy from the older bag and a green candy from the newer bag. The other probability is the probability that I draw a yellow candy from the newer bag and a green candy from the older bag. When we draw these two candies, what we get from one bag is independent of what we get from the other bag, and so we can use the multiplicative law of probabilities, which tells us the probability that I draw these candies is the probability I get a yellow from one bag times the probability I get a green from the other bag. Those probabilities are different for each of the hypotheses. In the first hypothesis, hypothesis A, the probability I get a yellow from one bag, the first bag, is 20%, and the probability I get a green from the other bag is 20%. Multiply them together and I get 4%. Under hypothesis B, the probability I get a yellow from the first bag is 10%, and the probability I get a green from the second bag is 14%. Multiply those together and I get 1.4%. So we'll plug those into the formula that we had going already. If you multiply it out and respect fractions, you get 20 over 27. That's the exact answer. The decimal approximation is that. And this is our answer. This is the probability that the yellow M&M came from the older bag and the green M&M came from the newer bag.